Now in this example I've got a single phase consumer's mains, a V75 consumer's mains, and it's sized at 16 millimeters squared to supply a maximum demand of 65 amps. The circuit route length is 35 meters, so I now need to check to make sure that my 16mm cable is large enough to suit volt drop requirements if my volt drop's not to exceed 2%. So 2% of 230 volts is 4.6 volts. Therefore, my calculation here for my VC formula is VC equals 1000 times 4.6, which is my 2% of 230, divided by the route length, which is 35 meters, and the maximum demand of 65 amps. Now, because I'm going to take this VC calculation, which is a single phase VC, so it's a single phase 2% of 230 volts, it's a single phase calculation, I'm going to take this VC to a three-phase volt drop table. I therefore have to multiply by 0.866. So here I multiply by the 0.866 so I can take my single phase VC calculation to my three-phase table. And that calculates out to 1.75 millivolts per ammeter. So in this case I'm using table 42, which is the three-phase volt drop for multi-core cables with circular copper conductors. So I've got a V75 cable, so I'm using the 75 degree column. Again, I'm then looking to find a VC that is lower than my calculated VC. So here, I look down the column to find something that's lower than my calculation. And for a route length of 35 meters, I have to upgrade my cable to 25 mil, so to ensure that I don't exceed a volt drop of 2% or 4.6 volts. So my 16 mil cable is now upgraded to 25 mil cable to suit volt drop requirements. Now in this example here, I've got a three-phase consumer's mains, 50 millimeter squared, 120 amps maximum demand, and over 25 meter route length. I then have a three-phase sub-mains, which is 25 millimeters squared, 80 amps maximum demand over a 35 meter route length. I then have a single-phase final sub-circuit, 2.5 millimeters squared, 16 amps over a 20 meter route length. So what I want to do here is then check the volt drops on each of these to ensure that I'm not exceeding 5% volt drop from the point of supply to the end of the final sub-circuit. So the VC for the 50 mil cable from the 75 degree column is 0.829, so we put that into our formula, which is the volt drop is the route length of 25 meters times the maximum demand of 120 amps times 0.829 divided by 1000 gives us a three-phase volt drop of 2.49 volts. Now then looking at the three-phase sub-mains, the 25 mil cable, so our VC there is 1.54. So we put that into our formula of 35 meters times the 80 amp maximum demand times the 1.54 divided by 1000 gives us a three-phase volt drop of 4.3 volts. Now we determine the volt drop for the single-phase circuit, our 2.5 mil cable with 16 amp maximum demand and 20 meter run. So we put that into our volt drop calculation. We use the 15.6, which is the VC for the 2.5 mil cable from the 75 degrees column. But because we're now using the VC from the three-phase table, we have to multiply by 1.155 to put it into our single-phase VD calculation. Okay, so that gives us a single-phase volt drop of 5.76 volts. We now have the issue of the fact that we're dealing with three-phase voltages and single-phase voltages, where we'll have a mismatch there. We can't just simply add those together. because the 5% of for a three-phase circuit, which is 400 volts, which is a 20 volt permissible volt drop, whereas with a single-phase circuit, 5% of 230 volts is 11.5 volts. So we have a mismatch there. So to overcome that, we have to convert our three-phase voltages into single-phase values. So we add the two three-phase voltages together, the 2.49 and the 4.3 volt three-phase values, to give us 6.79 volts. Okay. Now, so we have a total three-phase volt drop value of 6.79 volts. Now, to convert a voltage, a three-phase voltage, to a single-phase voltage, we use the factor of √3. So here we're showing the 6.79 divided by √3 will then give us 3.9 volts. Now that's the equivalent single-phase volt drop for that for those two lengths of three-phase cables. So we now have a single-phase equivalent of 3.9 volts. Now we can add the equivalent 3.9 volts to the 5.76 volt single phase, which then gives us a total of 9.66 volts volt drop on the single phase circuit, which is permissible because the as you can see, the 5% of 230 volts equals 11.5 volts. So our 9.66 volts is within that range. That concludes this section for this photo story on volt drop requirements. So applying volt drop requirements to the AS NZS3008 1.1 2009. So I'm Ian Evans. Thank you for listening.